So this problem, number 8, is about a Venturi tube, and I wanted to show you a real photo or a cross-section of one. This is a drawing here that I just downloaded from the internet. And as you can see, all a Venturi tube is a tube that has a varying cross-sectional area, and there's usually a constriction in the tube in the center, so that as the air flows through this tube, the volume is different. And as you know, since did I say volume? I didn't mean to say that. The velocity is different. So as you know, the mass flow rate, if the density doesn't change, the mass flow rate will be equivalent throughout this thing. Actually, the mass flow rate will always be the same, regardless of changes in density, because of the conservation of mass. But in any case, if the density is the same, we have the area times the velocity here, the cross-sectional area times the velocity, is equal to the cross-sectional area times the velocity here. Since this area is smaller, we expect higher velocity. The higher velocity, so in order to give the fluid the directional kinetic energy, you have to pay for it in hydrostatic pressure. So the energy from the hydrostatic pressure. So we expect the pressure in this region right here to be lower than the pressure that you see here. So let's go ahead and do the calculation, and we'll start with my awful drawing. Let's see. I think we'll start with my awful drawing. Okay. Get to this. Here we go. Okay. We've got this terrible drawing of the Venturi tube, and what we know about it is that it's 45 centimeters in this region. The cross-sectional area has a diameter of 45 centimeters. Down here, the diameter is 15 centimeters. And you could see that the flow results in the pressure differential that causes this head right here, which is 37.5 centimeters. Now, the thing that's tricky about this problem, in my opinion, is that the flow that we're looking at is flow not of air, but flow of water. Now, normally when it's just flow of air, you don't really worry about this particular air column, because or the fact that you have air throughout here, and then this right here is a liquid. I think in the problem it says this is mercury. Is it? Yes, this is mercury with a specific gravity of 13.6. And this here is water throughout. So in this particular problem, you have water in this region, and then you have mercury in this region. So how do you deal with that in the pressure differential? Well, first of all, we're asking for the volumetric flow rate. So we know that the answer is going to be in terms of meters cubed per second. We're expecting something like that. Now, how do we get there? Well, what we know is from, let's see, if this is incompressible flow, we know that the flow through this Venturi tube is going to be dictated by the Bernoulli relationship. So the energy is constant from what we might call point 1 to point 2. So if you recall, the Bernoulli relationship is something like this: P1 plus 1/2 rho V1 squared. Now notice that there is no change in Z, so I'm just going to drop out the Z term. Equals P2 plus 1/2 rho V2 squared. I'm presuming it's incompressible flow, so the density is constant as you go across here. So again, we're trying to get to the volumetric flow rate. If we knew the velocity in one of these areas, 1 or 2, we know that we can get the volumetric flow rate by simply multiplying the area times the velocity. So let's work on getting these velocity terms. So if we look at this equation right here, we could see that we don't have the velocity terms. We don't have the pressure terms. We could get the pressure differential. We could get difference between P1 and P2. So that would eliminate one variable, or two variables, and now we're left with V1 and V2. Now, the other relationship that, of course, we know from the continuity equation is that the area 1 times velocity 1 is equal to area 2 times velocity 2. So we can substitute for one of the velocities since we know the areas. So V1 is A2 over A1 V2. We can substitute for the velocities once we get that relationship, and then solve for the velocity, and then get to the Q value. Okay, so before I start crunching the numbers, myself, what I like to do is ask myself physically, what do I expect to get here? Well, physically, I'll say, just looking at this venturi tube, I know that the pressure here, pressure at 1, is going to be greater than the pressure at 2. I just know that pressure, because the velocity here, we know velocity 2 is going to be greater than velocity 1. And that's what causes the hydrostatic pressure difference. So we're expecting here velocity 2 to be greater than velocity 1. We're expecting pressure 1 to be greater than pressure 2. So I'm going to say pressure 1 minus pressure 2 is equal to, or 2 times that, is equal to rho times V2 squared minus V1 squared. V2 is bigger than V1. I'm just trying to work myself into a set of positive numbers here. So I'm going to do some substitution for V1 here and get, and maybe I'll move the density over here. Should I put the density over here? Well, I'll use this equation eventually. Let me actually turn my attention to getting this pressure differential. I need to get this pressure differential by working with what I've got going on here. Now, again, the goofy thing about that is that I have a situation where I've got water in this region and then mercury over here. So myself, kind of how I deal with this is I have trouble with the equations. I have to just kind of look at the levels. And I know in my mind that the height of a fluid is the thing that determines the pressure. And so if I go from this point, here, starting here, what I tell myself is the pressure there, whatever that is, I'll call it P1. I might start there, and then if I go down into the fluid, if I was a molecule moving down to the fluid, I know that my pressure would actually increase by the density of the water, rho g times gravity times the height of that column, 0.375 meters. That would give me the pressure at this interface between the mercury and the water. Well, then I know that as I go down into the mercury, my pressure further increases, but you can see that it decreases as I come back up, so that at this point over here on the other side, the same height, that's meant to be the same height, the pressure will be the same. So if I start there and then I go up into the mercury, I know that my pressure is going to drop. So I'm going to drop by the specific gravity of mercury, 13.6, times the rho of water times gravity, rho g, times the height, 0.375 meters, and that will get me to the pressure that I have at P2. So but what I really want to know is what's P1 minus P2. So if I now have P1 minus P2, I know that's equal to 13.6 times the density of water, 1,000 kilograms roughly per meter cubed. At different temperatures, it's different densities, but it doesn't it's, two in the third significant figure, times gravity, 9.8 meters per second squared times 0.375 meters. So that whole thing minus, let's see, I don't have room to write this. Actually, you can see this is 13.6. Here's the whole value here, this value. Can you see that? These are the same. So 13.6 minus one of those is just basically 12.6 of those. So I'm going to turn this term into 12.6 times that whole thing. So what do I get there? 12.6. Let me move. Can I go to another page? How do I do that? All right. So P1 minus P2 is equal to 12.6 times 1,000 kilograms per meter cubed times 9.8 meters per second squared. Is that right? Okay, so that's roughly, what is that? That is about 10,000 times another 10 is 100,000. It's about, okay, it's going to be about 1,100,000 kilograms, kilogram pressure, kilogram meters, meters per second squared is newtons per meter cubed. That's not right. I need to go back a page to make sure. 0.375 meters. See, I knew there was something was wrong. 0.375 meters. So that gives me, in terms of my units, that gives me meters times meters is meters squared divided by meters cubed gives me kilograms per meter second squared, or that's the same thing as kilogram meter per second squared, which is a newton, divided by meters squared. So all I did is multiply this by meters over meters to get this value. Newtons per meter squared. That is my pressure value. So about 1,100. 110,000 newtons per meter squared. Is that right? So this is about 10 to the 4, 10 to the 5th. Yeah. 10 to the 5th. Yeah. Okay, so that's P1 minus P2. Okay, so that's one value that we've got going on here. So what else do we need to do? Well, we need to put that P1 minus P2 here. That is 110,000 newtons per meter squared times 2 divided by this density is the difference in these velocities squared. Now I need to use this equation to substitute into this equation to substitute for one of the velocities. Let me keep going here. The next page. 110,000. You can speed this up. Okay, so 110,000 newtons per meter squared times 2 is 220 divided by 9.8 is about, I don't know, we're going to call that, just because we're approximating this, I'm going to be 2% off. This is going to be about 10. I'm going to drop that off, times that is 22,000 newtons per meter squared. I'm approximating, and the diameter is, we know that this diameter is 40, D2 is 15 over 45 is 1/3. So this is 1 minus 1/9. So 1/3 squared, 1/9. 1 is 8/9.